All right, we're looking at 2017 FRQs, and this is going to be page 24. All right, so at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. Internal temperature of the potato at time t minutes can be modeled by the function h, or h of t, that satisfies the differential equation dHdt, think of this as your h prime, equals -1/4 h minus 27, where h of t is measured in degrees Celsius and h of 0 equals 91. Okay, part A, write an equation for the line tangent to the graph of h at t equals 0. Use the equation to approximate the internal temperature of the potato at time t equals 3. Okay, so typically when we're thinking about writing equation of the tangent lines, we naturally gravitate towards thinking in terms of x and y, right? Find our order pair in terms of x and y. Our slope is m, and then point slope form, y minus y1 equals x times x, or m times x minus x1. Okay. The issue here is that everything is in terms of t and h, so we need to make that adjustment. Okay. So instead of x and y, we have to think in terms of t and h. Think of t as your independent variable and your h as your dependent variable. Okay, so we have to make that adjustment. Okay. So our order pair, instead of x and y, we have t and h, and our order pair is going to be 0, right? The problem says write the equation of the tangent line at t equals 0. So we know our order pair is 0, 91. That's provided for us at time t equals 0. Temperature is 91 degrees. Okay, so that's our order pair. Our slope is going to come from our derivative. Our derivative is this dHdt. And dHdt, we can plug in our order pair, t and h. So it looks like it's only going to take in h. So but I'm going to set it up that way and insert my variable into my derivative. So 91 replaces h, and I get -1/4 parentheses 91 minus 27. 91 minus 27 is 64. 64 over 4 is 16. And then I need to include that negative there. Okay, so we have our slope. And point slope form, we typically think of y minus y1 equals m times x minus x1. But we want to find our tangent line equation in terms of t and h. So instead of x minus x1, I'll use t minus t1. Instead of y minus y1, I'll do h minus h1. Okay, so now it's just going to insert the information I've gathered. 0, 91 will plug in for t1 and h1. -16 will plug in for m. And there's my tangent line equation. H minus 91 equals -16 times t minus 0. Solve for h. So that's my equation of the tangent line. And now I can evaluate my tangent line at, problem says, at 3. So it's kind of like linear approximation, except it's not a decimal. They're giving us a whole number, but we still go through the same steps. Plug 3 into the t of our tangent line equation, 43 degrees Celsius. Okay, part B. Part B says use d2h over dt2 to determine whether your answer in part A is an underestimate or an overestimate. Right? So d2h over dt2, that's basically saying find the second derivative. So to find the second derivative, I'm looking at my dh dt. This is at my derivative level. And I'm just going to find the derivative of this equation. That will bring me down to the second derivative. Okay, let's think in terms, though, that we're kind of in this related rates realm since we're dealing with dt here. So everything is in relation to time here. Okay, but we start off with dh dt. That's our derivative. I'm going to go ahead and distribute that -1/4 through, so I don't have to deal with parentheses. It feels a little bit cleaner without dealing with parentheses. So if I distribute the -1/4 through, I get -1/4 h plus 27 over 4. Okay, so now I'm going to find the derivative. Okay, so dh over dt turns into d2h over dt2. -1/4 h becomes -1/4, and then h becomes h prime. And the way we say h prime is we say dh dt, right? Everything is in relation to time. And the 27 over 4 goes away to 0. I want to know what is the second derivative at a particular time. But let's go ahead and make some substitutions here. dh dt is a little bit easier to work with variables in terms of time. So I'm going to replace my dh dt that's showing up in my second derivative in terms of h. So I'll bring my original dh dt expression, defined expression, back into the fold here. So dh dt is defined as -1/4 h minus 27. Okay, so this is my full second derivative in terms of h. Let me do some cleanup here. Multiply the -1/4 together, I get positive 1/16. So I have my second derivative, my h, which is my temperature that I gathered at 3 minutes. Is 43 degrees. So now I can enter that 43 degrees into the second derivative. And the only thing I care about is whether it's positive or negative, right? And because my second derivative is positive, I know visually that means this graph has a concave up shape. If I have a concave up shape and the line tangent is skimming the surface of that curve, we know that this tangent line is going to have to sit below the curve, because if I have a concave up graph, no matter where my tangent line is, it's always going to sit below the curve. So therefore, since my h function is concave up, my approximation is therefore an underestimate. Okay, does that make sense, Vinesh? Okay. Okay, part C is where we move into working on solving the differential equation. So part C says we're given our differential equation, dg dt equals negative parentheses g minus 27 to the 2/3. So typically, I know we're used to solving differential equations in terms of x and y, and I always say, hey, put the y's on the left, put the x's on the right. But here, the variables aren't as familiar to us. However, you know that if you see some strange variables, it'll always be anchored with the variable time, t. So if you see time t, you know that, okay, that means that my time is my independent variable. I'm going to treat time like I would x. And whatever the variable I don't recognize, this g is basically my y. So I'm going to go through the same steps like I would solving differential equations. I'm going to put that right side over 1, and I'm going to cross multiply. Okay, cross multiply. It may not separate the variables, but it will get the dg in the right spot. It'll get my dt in the right spot. So cross product, 1 dg equals negative parentheses g minus 27 to the 2/3 dt. Right? I want to move this g minus 27 to the 2/3 over because I want the g's together and everything else on the right. Now, we can actually do this. I'm going to hold that negative on the right side. I'm not going to move that negative. It's going to come back anyways. I only want what's on the left, what the bare minimum that's required on the left. Everything else I would prefer to leave on the right side. So I'll divide that parentheses over. So g minus 27 to 2/3 is in the denominator. This is going to be a use substitution problem, but I know that eventually I have to go through power rule, and I would need that parentheses to be in the numerator. So I'm going to just go ahead and do that. Move that g up to the numerator. So g minus 27 to the negative 2/3 dg equals integral of -1 dt. And I know I can go through use substitution here, but the right side is set up nicely for power rule. Okay, so my u value is g minus 27. My derivative, du dg equals 1. I'm not going to have any leftover coefficients, but it's going to work out nicely where all I'm doing is just doing power rule u to the negative 2/3. So go through power rule, add 1 to the exponent. Negative 2/3 plus 3/3 is 1/3 divided by that new coefficient. And then the right side is power rule. -1 becomes -1t plus c. Okay, flip the 3 up to the top. Bring the original variables back. So I'm left with 3u to the 1/3. Replace u with g minus 27. -1t plus c. Okay, so now my calculus is done. I'm just trying to figure out how can I solve for g and how can I solve for c. Okay, so I'm going to go ahead and see if I can get the c out of the way. I have my order pair. Order pair that's given to us is (0, 91). So t equals 0. When t equals 0, temperature is 91 degrees. Make that substitution, 0 in for t, 91 in for g. So I'm just trying to solve for c here. 91 minus 27, again, is 64. Cube root of 64 is 3. Sorry, cube root of 64 is 4. And then -1 times 0 is 0. So 3 times 4 is 12. So there's my c value. Now that I have my c value, I'm going to insert that value that I found into where I made this initial substitution. And now the only thing left to do is to solve for g. Okay, 12 goes in for c. And now let's see what I can do here. I can divide by 3, cube both sides, and add the 27 over. So divide the 3 over. Cube both sides. And then final step, let's add that 27 over to the right side. There we have our g of t. Finally, use this based on this model. What is the internal temperature? Yeah, what's the internal temperature of this potato? Insert 3 in for t. Internal temperature when at 3 minutes is 54 degrees Celsius. Okay. Any questions here? Okay, good with 4. All right, number 5. All right, number 5. Okay, number 5, two particles move along the x-axis. Between 0 and 18, the position of the particle is given by x of t, and this subscript p just indicates we're talking about this particle p. So we have position of one particle, but then for q, we're given information about its velocity. So we have two different particles, and then we also have two different functions. One is position for one, and the other is velocity for the other. So eventually we may have to match them up. Okay, particle q is at position x equals 5 at time t equals 0. Okay, between 0 and 8, when is the particle p moving to the left? Okay, so we know that our particle p is moving to the left whenever our velocity is negative. So we first have to create our velocity sine line, right? Let's create our velocity sine line. So we need to first find the derivative. From the derivative, find the critical points, populate the sine line, and then test the intervals. Okay, so right, so we need to find the derivative first, right? We need to make our way down to the velocity function. So x of t is natural log of t squared minus 2t plus 10. That's our position function for particle p. We need to find the derivative or the velocity. The rule for natural log is u prime over u. Okay, critical points. Where is velocity equal to 0? So velocity equal to 0 when the numerator is equal to 0. Okay. 1 second here. Okay, so we just focus our attention on the numerator to find our critical points. Okay, factor out of 2. E equals 1. Okay, so create our velocity sine line. All right, we know that with natural log functions, nothing can exist to the left of 0. We're kind of bounded by 0 as our left endpoint. Okay, we know we're going from 0 to 8. And there's one critical point, and that's at 1. Between 0 and 1, we can choose a value to test. We can test 1/2. Between 1 and 8, we'll test 2. We're testing this against our velocity function. So 1/2 in for t, I get 1 minus 2, that's negative. And then 1/2 squared minus 1 plus 10. This 10 is such a large value. This is going to be positive. So I get a negative or a positive, which is negative. So my particle is moving left. If I plug 2 in, 2 times 2 is 4. 4 minus 2 is 2. 4 minus 4 plus 10 is still positive. This is positive or positive. The particle is moving left in this interval from 0 to 1, since v of t is less than 0. Okay, now we know that at 1, the particle is not moving, so it makes sense that we don't include 1 in terms of moving left. But 0 is not a critical point. 0 is a starting point. So we need to test 0 to see whether, because maybe the particle is already moving when the timer starts. If it is, then we may need to include 0 as part of our domain. So let's test it out. So if I test 0 into velocity function, let's see what happens. If I plug 0 into the velocity function, I get 0 minus 2, which is negative. 0 minus 0 plus 10. Okay, that's positive. Negative or positive is negative. So that means this particle is already moving at 0. So we need to include 0 as part of our domain for the particle moving left. Very subtle thing, but we need to include that as part of our answer. Okay, so we have the sine line for particle P. Let's move on to the second particle. Okay, for B, it says between 0 and 8, find all the times when the two particles travel in the same direction. Okay, so we have velocity for particle P. We have all that filled out. In order to figure out when the particle is moving in the same direction, we also need to create a sine line for particle Q. We already have the velocity function, so no need to find the derivative. We can just set this equal to 0. Multiplies to be 15, adds it to be negative 8. Solve for t, we get 3 and 5. Zero and 8, 3 and 5 shows up. And critical points to test. So I'll test 1, I'll test 4, and I'll test 6. Test it against particle Q's velocity function. 1 in for t. 1 minus 5 is negative. 1 minus 3 is negative. 2 negatives gives me positive. Four minus 5 is negative. 4 minus 3 is positive. Negative times positive is negative. 6 minus 5 is positive. 6 minus 3 is positive. So positive. So if I line everything up here, when are they moving in the same direction? From 0 to 1, they're not going to be matching. From 1 to 3, they will be matching. Okay, from 3 to 5, it doesn't match, but then from 5 to 8, they match again. So 1 to 3 and 5 to 8. Now 8 is not a critical point, 8 is an endpoint. So we need to test 8 for both of our particles, see what happens there. So if I enter 8 into my velocity function, I get a positive value. So it's still moving right at 8. Let's see what happens 8 for my first particle Q. If I plug in 8, I get 16 minus 2 is positive. Denominator gives me 64 minus 16 plus 10 is positive. So it looks like 8, they're still moving, and they're both moving the same direction. So we need to include a bracket for 8.
If they weren't moving the same direction.
Yeah, we'll do parentheses.
Mm-hmm. But I wouldn't still include 8.
Oh, you mean if this wasn't the same direction? Yeah, then I would have stopped it at from 1 to 3. Yeah. Okay, same direction because they both have the same velocity sign. Same velocity sign. That means they're going the same direction. Okay.
Oh, yeah, no, when it was like, so if it was like past 5, like let's say for 6, it was still positive. Then for 8, it was different. Would I just put 5 to?
Okay. Yes, but that's only if we have kind of critical points to kind of help us see it, right? So because there's no critical points that show up, we're not going to deal with 7, right? There's not going to be a random number that shows up if it's not in our sine line already. Okay, part C, find the acceleration of particle Q. So we have to move to the second derivative for particle Q. We got the first derivative, we'll find the second derivative. Is the speed of particle Q increasing, decreasing, or neither at time t equals 2? Okay, so we know that if we're dealing with the speed of a particle, we have to, or if speed is increasing or decreasing, we have to compare the signs of their velocity and acceleration, right? Same signs for velocity and acceleration would mean increasing speed. But if one is positive and the other is negative, then speed will be decreasing. So we find the acceleration function for particle Q. So derivative of t squared minus 8t plus 15 is 2t minus 8. So let's find the velocity at 2, and let's find the acceleration at 2. Velocity at 2 is going to be positive 3. Right, we plug 2 in here. 2 minus 5 is negative 3. 2 minus 3 is negative 1. Negative 3 times negative 1 is positive 3. So velocity is positive. Acceleration, on the other hand, if I plug 2 in for acceleration, 2 times 2 is 4. 4 minus 8 is negative 4. Positive velocity, negative acceleration, opposite signs. Speed of the particle is decreasing. Since velocity and acceleration have opposite signs. Part D. Find the position of the particle Q the first time it changes directions. So particle Q, first time it changes direction, it's going to be at 3 based off our sine line. So if I want to find the position of the particle at 3, I'm going to go through the formula that I've used a lot with particle motion. Final position equals initial plus displacement. Okay. So final position equals initial plus displacement. The first time particle P changes signs, changes direction is at t equals 3. So I want to figure out what x of 3 is. I'm going to start at x of 0. Particle Q. Oh, and then they tell us at the beginning, particle Q has position of 5 at t equals 0. So we are given a starting point. So x of 0. And then once we have our starting point, we have to bridge the gap between starting and ending locations, ending time, so we can find out how much progress has been made. So the depth integral from 0 to 3 will give me a v of t, will give me displacement. Okay, x of 0 is 5. And then we got to take the definite integral from 0 to 3 of t squared minus 8t plus 15 dt. And this is number 5, so no calculator. We got to work this out by hand. So, but the nice thing is, it's easy power rule, just a little bit tedious. I have to go through each of those terms. T cubed over 3 minus 8t squared over 2 plus 15t. And then we work in our 3 and 0. Okay. Upper bound first. Minus parentheses lower bound. The 0 will wipe everything out, which is nice. And then we're just trying to merge and combine all these numbers together. Okay. 3 cubed over 3 is 9. 4 times 9 is 36. 15 times 3 is 45. Make sure we add it on to our starting point. This is the progress we made, and we get 23 as the location of this particle 3 seconds in. Particle Q. Good. Okay, number 6. Okay, number 6, let f be the function defined by f of x being cosine of 2x plus e to the sine x. Let g be a differentiable function. The table above gives the value of g and its derivative, g prime, as selected values of x. Let h be the function whose graph consisting of 5 line segments is shown. Find the slope of the line tangent. So to find slope, I first have to get to the derivative. So we'll start with building our way to f prime. Okay, chain rule. Cosine of u becomes negative sine of u times u prime. E to the u is e to the u times u prime. So we build our derivative that way. Negative sine of u times u prime. E to the sine x becomes e to the sine x times cosine x. Replace every x with pi. And then try to get it down to a numeric value. So sine of 2 pi is 0. E to the sine pi is 0. E to the 0 is 1. Cosine of pi is negative 1. Zero minus 1 is negative 1. So my slope of the f graph at pi is negative 1. Okay, part B. Part B says, let k be the function defined by k of x equals h of f of x. So here we need to recognize that this is a function within a function. We got to go through chain rule. So outside's derivative times inside's derivative. Outside is my h bracket, and my inside is the f of x. So we take turns with their derivatives. H's derivative is h prime. F's derivative is f primes. We have to go through and make sure we follow the proper procedure for chain rule. Outside's derivative is h prime of f of x. We leave that f of x intact. We're not ready for it yet. Once we get out of that bracket, then we multiply by the inside's derivative times f prime. Okay. Make sure we build our chain rule correctly. And now we can go through and replace every x with pi. Okay, so k prime of pi is equal to h prime of f of pi times f prime of pi. Okay, that's a bit messy, but let's start with what we can do here. Why don't we find this f of pi here so that we'll have an easier time trying to figure out what to do with this h prime of this bracket. So f of pi just means I'm going to insert pi into the original f of x equation. Okay, so place every x with pi, so cosine of 2 pi plus e to the sine pi. So I have that worked down here. F of pi is cosine of 2 pi plus e to the sine pi. Cosine of 2 pi is 1, sine pi is 0, e to the 0 is 1, 1 plus 1 is 2. So f of pi gets replaced with 2. All right, are we good there?
Yeah.
Okay, so now we have an easier problem because now I just have to figure out what h prime of 2 is and also figure out what f prime of pi is. So h prime of 2 is looking at the h graph and seeing what is the slope of the h graph at 2. So at 2 is part of this decreasing slope, negative slope. So I just have to figure out the slope of this line segment. So starting at the ends, I go down 1/3. My slope is negative 1/3. F prime of pi, I can go to part A, right? I gather that from part A, which is negative 1, so I can bring that down. So negative 1/3 times negative 1 is positive 1/3. Part C. Let m be the function defined by g of negative 2x times h of x. Find m prime of 2. Okay, so we need to recognize that these are two distinct functions. We got to go through product rule and chain rule. Good. Yeah, that g of negative 2x is going to be a little bit of chain rule here. So there's product rule going on. And there's also a little bit of chain rule. Okay, we got to get all this worked out before we do anything with that m prime of 2. Let's find m prime of x first. Okay, so first things first, let's find the derivative of g of negative 2x. G of negative 2x is derivative. Outside's derivative times inside's derivative, so g becomes g prime. We hold that negative 2x intact times the inside parentheses derivative. Negative 2x becomes negative 2. H of x stays plus g of negative 2x times the derivative of h of x, which is h prime. Okay, replace every x with positive 2, now that we have our full derivative. So I get g prime of negative 4 times negative 2 times h of 2 plus g of negative 4 times h prime of 2. So all I'm doing is replacing every x with 2. And now let's see what's available for us to solve. G prime of negative 4, that's just going to be from the table. H of 2 is just an order pair, y value from the h graph. G of negative 4 is a point from the table that we can gather. And h prime of 2 is a slope of the h graph at 2. Okay, so piece by piece here, g of prime of negative 4 from the table, we can see that's equal to negative 1. Okay. G prime of negative 4 is negative 1. keep the -2. H of 2 is -2/3. Now this feels a little bit strange here, but we know that the slope is -1/3, so it's going to go down 1/3. It's going to be 3 units over before it reaches all the way down -1. So each time we go through one x value, it's going to go down by 1/3. So it'll go down -1/3, -2/3, and finally -3/3. So we know that's going to end up at -2/3. G of -4 is just from the table, which is 5. And then h prime of 2 is the slope of the h graph at 2. We can just do rise over 1. The slope is -1/3. Okay, clean all that up. We get 4 times 1, or -4 times 4 times -1, which is -4. For -4/3 minus 5/3 is -9/3, which is -3. Okay, questions so far? Good. Part D. Is there a number C on the closed interval such that G prime of C is equal to -4? So if we're looking at the G prime table, we can see that it doesn't reach -4. Doesn't mean that it's not there. It's just that we can't use IVT to get us there. But we do have G of X, and G of X and G prime, there's that slope and derivative relationship. So if we think of it in terms of G of X, we can think of it in terms of, okay, can I guarantee a derivative of -4? Can I guarantee a slope of -4 between -5 and -3? Well, if I can get my order pairs to show me a slope of -4, then there must be a point somewhere along the curve where the graph is going to experience an exact slope of -4. So this is really kind of leading us down the road to apply mean value theorem. So let's test it out. Well, first off, we know G of X is differentiable, therefore it must be continuous. So our conditions are good to go with mean value theorem. Okay, we take our endpoints that's provided for us, -5 and -3, and we'll do G of -5 minus G of -3 all over 5 minus -3, or vice versa. We get 2 minus 10 divided by 2, which is -8 over 2, which is -4. So because the slope between the -5 and -3 shows a -4, we know there must be a point on the curve somewhere in that interval where the slope is going to have to match exactly -4. And therefore, by MBT, there's at least one value C on the interval such that G prime of C is equal to -4. Okay, any questions with 4 through 6 FRQ? Okay. Good. So tomorrow we'll go through 2016 FRQs. Okay. And that way we would have seen all these FRQs from the most recent years, and that should give us a good feel for when we approach these FRQs on Monday.